Welcome to Smart Integrators short webinar about teaching communications. As we look at the technical landscape that graduating engineers are confronted with, we can see that wireless communications are becoming more complex and more ubiquitous, from industrial applications like near-space communications and the Internet of Things, to end-user applications like medical devices and 5G. Wireless communication systems are everywhere in our modern world. And yet, despite the omnipresence of wireless communication systems, the path for engineering students to begin designing them is unclear. The traditional approach to teaching wireless communications is to present students with a large amount of theory, without little application to a physical system. While theory is important, a diet of nothing but theory can intimidate, confuse, and deter otherwise motivated students from becoming successful engineers. Especially within wireless communications, we find that the theory is complex and convoluted literally. Complex numbers, real and imaginary concepts, complex permittivity, and high-frequency physics and material science. Within engineering, wireless communications has the reputation of quantum mechanics for mind-bending concepts. Other areas like control and fluid mechanics have their own complex formula too. But compounding the issue for wireless communications is that the reality is intangible. This is a bending beam under force, or a mast flying through the air. And to date, no student has ever come onto a communications course having physically seen a GSM or FM signal. Without experience, theory is tough to relate to. We have to bring experiential learning to communications by providing visibility of real-world signals to help students understand abstract theory, while preparing them for research in emerging trends like 5G. So here is a comprehensive map to all of those turnkey solutions we have for teaching communications. What we are going to do for the rest of the presentation is step into each one in detail, and then take a brief look at some of our work with wireless communications research. Let's start with fresh communications engineering students. They are eager to experience the practical side of signals and systems. They need to create real signals and visualize it. They need to interact with these signals and feel the impact of the theory they apply through real hands-on exercises. This objective is successfully achieved with National Instruments' main academic platform, LVIS 3, with its add-on boards. Let's have a quick overview on LVIS 3. With its programmable Xilinx 7020 FPGA, NAI LVIS IE addresses engineering curriculum by integrating project-based learning, teamwork, and design with course-specific application boards and labs developed by experts from education and industry. NAI LVIS IE enables educators to scale to future multidisciplinary applications, driving student employability. The NAI LVIS 3 promotes teamwork and collaboration by providing Windows and browser-based connectivity to 7 benchtop quality instruments. These include Bode Plotter, IV Analyzer, 4-channel oscilloscope, a function generator, variable power supply, digital multimeter, and a pattern generator. The NI LVIS 3 also includes analog and digital input and output channels, power supply, 8 lids, 2 buttons, 2 switches, 3 potentiometers, 3 test point, audio in, audio out. What really empowers LVIS 3 is its modularity. The add-on boards extends its capabilities to meet different courses' needs. When teaching communications, there are 3 boards developed by Emona that pair with LVIS to cover 3 crucial courses. These are the Daytex, Photex, and Segex boards. The Emona Communications Board is an add-on application board developed to teach introductory digital and analog communications topics. The Emona Communications Board offers students the opportunity to build, measure, and experiment with communication systems that are commonly only theorized in textbooks, including various modulation schemes, superheterodyne topology, restoring recovered data, and more communications architecture topics. The second board of Emona is the Fiber Optics Communications Board. This trainer provides students with a basic understanding of many fiber optic communications-related concepts like PCM encoding, PCM decoding, sampling and Nyquist in PCM, time division multiplexing, TDM, optical digital filtering, splitting, and combining, fiber optic bidirectional communication, wave division multiplexing, and optical losses. The third board is the ENONA SIGEX board. The Amona Signals and Systems add-on for the NI Elvis 3 is designed to help students experience at first-hand the interaction between the theory and mathematics of the digital signal processing, circuit analysis, and signals and systems textbooks, with the real world of hardware and of signals in wires and waves. The accompanying 16-experiment lab manual covers introductory level experiments designed to provide hands-on exercises covering most of the key concepts and challenges in an undergraduate signal processing and signals and systems courses. Now, students are empowered with solid understanding of basic signals, communications, and systems. It will be smooth to move them to the next challenge. Using the same Southwest platform, they will be working with more practical industrial communication SDR system, which is USRP. The Software-Defined Radio Device Bundle is a turnkey solution for wireless communications teaching that helps students experiment with real-world signals using LabVIEW software and USRP hardware. The Software-Defined Radio Device Bundle is a hardware and software bundle that includes USRP software-defined radio devices, LabVIEW software support, and turnkey courseware. The bundle also includes components of a lab station designed to help students gain hands-on experience with a live communication link between USRP software-defined radio devices. By introducing hands-on communications engineering earlier to undergraduate students, you can build experiences that connect the teaching lab to research and industry. Learn how the University of Southampton creates a pipeline of students proficient in software-defined radio, SDR, so that graduates can apply engineering knowledge to advanced, cutting-edge problems like 5G from day one of their careers. The 12 lab projects should be sufficient to support a one-semester course. For a one-quarter course spanning 10 weeks, Labs 3 and 4 can be omitted without compromising continuity. Designed to be an introductory course that takes students from the group up, with a focus on system design and associated modulation schemes. No prior SDR, hands-on, or LabVIEW experience is required of the students. Included course labs are. Now let's have a look on a real-life challenge faced by the University of Southampton and how they were able to solve it. This university has been looking at new and innovative ways to teach the principles of communication at a time when there is significant interest in wireless technologies. Previously, wireless communications education has significantly focused on theory with a need for a more practical approach to teaching this topic. The solution. The University of Southampton has revolutionized the way it teaches wireless communications. Central to this is their hands-on, practical approach to learning. Students learn the theory behind a concept, and then get hands-on with hardware for practical learning. The university uses this USRP-based approach to great effect in their wireless communications education. The solutions you have seen so far are great for teaching the core concepts of communication systems. And it's time to open the door for students to learn more about advanced communication systems using digital schemes like OFDM. Students now can use LabVIEW efficiently and ready to move to real-time and FPGA leverage for modern communication systems. An advanced version of USRP is used, with same graphical design approach. Digital Communications course is authored by Prof. Robert Heath of University of Texas, Austin. The course is well-suited to graduate studies in wireless communications and focuses on the real-world challenges faced by physically separate transmitters and receivers, featuring 10 lab classes to fill one semester. The course deep dives into algorithm design for modulation and demodulation, pulse shaping, energy detection, equalization, frame detection, introduction to orthogonal frequency division multiplexing, OFDM, frequency correction and sync, and OFDM channel coding. A sample lab is available for free download. The complete manual is included in the NI Digital Communications Teaching Bundle. One more university that has shared success story using LabVIEW and USRP in digital communications teaching is Stanford University. Dar Sachinkati from Stanford University has claimed that, with the software and hardware combination of LabVIEW and the NI USRP, students were able to build and explore each element of a complete communication system signal chain. So now that we have introduced NI LabVIEW and how it can be used along with the power of graphical system design to create real-world wireless systems, we can go through and look at how we at NI build a bridge from introductory communications through university courses, all the way to working in industry and research. The typical communications design process can be broken down into 3 distinct stages. The algorithm development is done by a research team, and this process usually starts in ATL software. The algorithm is then thrown over the proverbial wall to be mapped to the specifications of the hardware. This team, the system design team, translates or converts the algorithm into a different language that can map to hardware. And finally, a different team prepares the design for implementation on real-world I/Os. The disconnectedness in this process, and how disparate the tools between them are, is the biggest roadblock to speeding this prototyping process. The ideal solution would be for a single tool to span this process and allow each team to work within the same tool on the same design, eliminating the costly code translations. The platform explained earlier enables wireless design and test in new technologies like 5G and 6G communications, promising new levels of connectivity for an array of use cases. Through our solutions, students is exposed to enabling technology breakthroughs and delivery of next-gen devices at scale. Our approach equips engineers with fast and flexible tools to stay at the forefront of these advances in wireless. Lund University was one of the first to build 5G complete system and is actively using it for massive MIMO research. They also created a custom patch antenna array, allowing for testing of multiple shaped arrays, including 25x4 and 10x10. Results are announced at GoBeCom 2014 in Austin. Having hands-on experience with benchtop instruments and engaging with each specific device has always been an interest to many instructors, as well as students, as to maintain the engineering origins, and lets the students first engage with each instrument individually before moving forward to deal with them all in a single embedded device. RIGOL provides wide range of affordable high-quality benchtop measurements instruments. Waveform generators and RF signal generators are commonly used in communications classes. RIGOL offers wide variety of signal generation instruments that meets the need of every communications laboratory. On the measurement side, RIGOL offers wide-frequency spectrum analyzers that operate up to 75 GHz, and for sure, they are controllable using LabVIEW for complete instrument control. With RIGOL digital oscilloscope operating in a bandwidth up to 2 GHz, students can easily perform electronics measurements and waveform measurements on analog and digital circuits. In addition, RIGOL digital multimeter works in the range up to 65 digits, measuring and verifying multiple electrical stimuli, including voltage, current, and resistance. So that was a brief video describing how Smart Integrator solutions in teaching communications are being used to bridge the gap between theory and real-life applications, taking students from basic introductory levels all the way to more advanced complex topics and giving them all the tools they need. I hope you have enjoyed this video. See you soon. If you have any question, please don't hesitate to contact us. Thank you.